Hello, my name is Daniel, and in this video I want to present the results of my HSDIP paper about dominance pruning in decoupled search. Let's briefly clarify context. We are in classical planning, we have multi-valued variables, so FDR or SAS+, and we do decoupled search. In particular, we are interested in avoiding repeated work during a heuristic search. Typically this is done via duplicate checking, where when you explore the search space behind the initial state, so you generate the extra successors, and you see a state that you've already seen before, here as 1, then you actually want to ignore the state and everything that comes behind the second copy, because you want to avoid to repeatedly handle these states. So you continue without considering the second copy of S1 anymore. Things become more interesting if you do, for example, a star search with a heuristic and a non-trivial cost function. So assume you reach the second copy of S1 with a g-value of 2, and you've already reached S1 before, but it has a g-value of 5. Then you actually want to keep the second copy to guarantee optimality, and you want to prune the first state. In decoupled search, things become a bit more complicated, because here search node doesn't correspond to a single state, but to a set of states. So here S1, S0, and S2. And transitions basically move from one set of states to another set of states, where these sets may overlap or not. If you do a star in decoupled search, then as before, you have basically costs attached to the edges, and additionally you also have prices in these reached states. So basically in the initial state, the component or the member state S0 has the cost or price of 0, and you could buy the state S1 at the price of 2, and if you go to the successor up here, then you definitely have to pay a cost of 2, which is like the g-value of this decoupled state. And if then you want to reach the state as 2 here, you have additionally to pay a price of 1. So given that decoupled states are way more complex than standard states, and also the cost function doesn't make it any easier, the question is how powerful can exact duplicate checking be here actually. So what's the chance that you find the same decoupled state with the same prices again during search? Before we go into the details of how this is done, I'd like to briefly recap the basics of decoupled search. So here's our most favorite transportation example, where we have a truck and 4 packages. And the interesting thing here is the causal graph, like the dependencies of the variables in this task, which is basically the packages being dependent on the truck, but they're conditionally independent of each other. And in decoupled search, we exploit this by instantiating the center, so here the truck, to break these conditional dependencies. More specifically, we search only over center actions, which in our case will be drive actions, and we handle each leaf component, so each package here, separately. So to make this example more explicit, let's say we have this sequence of drive actions, and then what we can do is basically for package 1, we could choose to load it into the truck when both are still in L1, then we drive the truck to L2, and then we unload the package. Alternatively, we could, along the sequence of drive actions, choose to load it initially, drive to L3, and only then unload it. Similar for package 3, for example, once the truck has reached L3, the package can be loaded. And once the truck is in L2, so it's driving back from L3 to L2, we could choose to unload it here. Alternatively, we could also unload it in L1. And the important observation here is that we can choose any of the paths A or B for the packages 1 and 3 independently of what we choose for the other package. And this allows us to maintain these compliant paths separately for each leaf or for each of our packages here. How's that reflected in search nodes, so in decoupled states? Well, every decoupled state consists of a center state, and for each leaf, a pricing function, which doesn't really contain these compliant paths anymore, but only their cost. So if this is our initial state of the task, then this is what the initial decoupled state would look like. In the center state, we have that the truck is in L1, and for each of the packages, and for each state it can reach, we have basically an integer which tells you which tells us the price that we need to pay to reach that leaf state. And initially, since the package is in L1, there's no price we have to pay to get it there. On the other hand, to load it into the truck, we would have to do one action, so cost of run, and this is the price of having package run in the truck in the initial state. Now, this decoupled state contains 4 explicit member states, which is basically all combinations of having packages 1 and 2 either in L1 or in the truck. And these have the corresponding costs of 0, 1, or 2, depending on which combination we choose, which is basically just the sum of the prices of the leaf states that we choose to be reached. Now, what if the decoupled state is not actually the initial state, but was reached on some path, so it has some g value? Well, then the cost of the member states of the decoupled state are basically computed by adding the g value to their price. And this is important because it captures all the cost that we have to spend to reach this member state in this decoupled state here. So let's get back to dominance pruning. How do we do that? So this is basically the standard variant that has been around before. We say that a decoupled state S dominates a decoupled state T if the set of reached member states is a superset of the ones of T. And for all leaf states, the price that they have in S is lower or equal than the price that they have in T, where this blue part is only actually needed for optimal planning. Then a state T can be pruned if there exists a previously visited state S, such that the dominance relation holds, so S dominates T. And again, in the case of optimal planning, S was reached with a g value that's most as high as the g value of T. To make an example, again with this decoupled state here, the important thing is that dominance can be computed component-wise. So we never actually want to enumerate all explicit states contained in a decoupled state, because these can be exponentially many. And we want to do all operations based on the components. And we can do that here because all the prices of 2 decoupled states can be looked up in the pricing function, and we can, for each leaf, compare these prices. No need to enumerate all explicit states. So let's make some example. We have 2 decoupled states here, and the question is, does one dominate the other? Okay, that one's easy. No, because here we have state S2 reached, and here we have state S4. So this subset relation doesn't hold, and there's no dominance. If we removed S2 here, then the right state would actually dominate that one, because all states that we have on the left are also there on the right, and they have at most the cost that they have on the left. A second example, what about this case here? Clearly dominance holds because the set of states are equal and all prices are lower or equal on the right. So again, what we can see here is that duplicate checking will not be very good in decoupled search, because what we would require is that the state sets are equal and all prices are equal. So a natural question would be then, why would we actually want to do duplicate checking in decoupled search? And the answer is efficiency. So if we compare 2 decoupled states, then what we need to do is for all visited states with a lower g value, we need to iterate over all prices of all leaves and compare them to see if a state is dominated. Now this obviously has a big computational overhead compared to duplicate checking, where you can just do hashing. With this, let's jump into our first contribution, which is actually a transformation of decoupled states, which we call the g-value adaptation. And the idea of this is to move as much of the price of the leaf states into the g-value as we can. In our example here, you see that there's 2 leaf components, namely P2 and P4, which have a minimum price that's greater than 0. For P2 it's 1, and for P4 it's at least the price of 2. Now what we can do is we can increase the g-value of the decoupled state by 3 and deduct the this from the prices of the reached leaf states. So what you see is that, in fact, the total cost of all reached member states of this decoupled state will not change, but we just move cost from the pricing function into the g-value. Why would we do that? Well, there's a couple of reasons. So one thing I need to mention is that decoupled heuristics work on the prices, and the lower the prices are, obviously the lower the heuristic will become. And in turn, we will get a higher g-value. So this is obviously good for type breaking in A star. Additionally, the g-value is always completely taken into account by the heuristic, while for heuristics, this might not necessarily hold. So they might not be able to capture everything that's incorporated in the prices. Think of blind search as an example, where all prices are basically ignored. So this is like basically lots of information that we could use for pruning. That's just or for search guidance also that is just not used, and this is obviously not good. Our second contribution is to make the dominance pruning actually more clever. So assume we have these two decoupled states here, where one is reached with a g-value of 3 and the other one with a g-value of 1. But the prices in the state with lower g-value are all higher than the one on the left here. So basically, although it has a lower g-value, because of the higher prices, we cannot do any pruning. And this is because although all member states on the left have a cost of 7, and all member states on the right have a cost of 21. So although we know that all member states here are reached with a higher cost than on the left, we cannot do any pruning. A second example would be this one here, where we have a g difference of 9, and we have two leaf factors where the prices differ. So they are equal for P1 and P2. Say for P3, all leaf states have a price that's by 1 higher than the one on the right, and for P4, there's one leaf state where the price is higher by 9. Now, when you do the math, which is obviously not too complicated, you will see that still all member states on the right are reached with at most the cost that they have on the left. So we could prune the left decoupled state. And we actually want to have a dominance relation now that's able to tell us just that. So we still need the subset relation of the reached member states, and now we actually want that all member states have a lower cost in S, where this includes the g-value in the comparison. So to prune a state, we can now basically use all previously reached decoupled states, and we do no longer have to restrict to the ones that have been reached with a lower g-value. How is this done? Well, we obviously, as I said before, we don't want to enumerate all member states on the left and all on the right and compare their prices individually, but we want to do this component-wise. And we can simply do this by only computing the maximal price difference maximized over all member states. And we do so by just per component see where the prices differ the most. And they don't differ in P1 and P2. For P3, on the left, they're always higher by 1, and for P4, now here's the interesting case. There's one member state or one leaf state, sorry, which is super expensive at a cost of 10 compared to the cost of 1 here. But again, I mean, if we do the math, we see that the member state on the left-hand side would have a cost of 15, where on the right-hand side, even the most expensive one only has a cost of 14. So we can prune the left-hand state. So the important thing is here that we can do this really component-wise. We just, per component, we look for the leaf state where the difference is maximized. Then we sum up all these maximal differences and see if they are lower than the difference in g-value. So let's look at some experimental results. Here for optimal planning, where this is really the most crucial, like strong pruning has the highest influence in optimal planning, because you need to search quite large search spaces. So on the left we have blind search, and on the right we have A star with LM cut. where what I didn't tell you before is that we have also implemented some optimizations that are just doing the dominance check in a more clever way. And these, compared to the baseline pruning, already have like a mild advantage. But compared to the G adaptation and also the total cost comparison of the member states, this is really has really strong results. So for LMCut, we distinguish. So this column here basically shows only the G adaptation, and the right one shows the combination of both. And here we get a total improve of 21 instances, which is quite good. I also want to show you briefly that duplicate checking in comparison to dominance pruning almost never pays off. So obviously the pruning is weaker, and the more efficient computation doesn't pay off. If you combine duplicate checking with the more fancy G adaptation and with the implementation of optimizations, for blind search you can get somewhat close to the baseline again. And for LMCut you can actually beat the baseline, but you're still far away from the fully fledged dominance pruning that includes all the features. So finally, I'd like to show you some search space and runtime data. So on the left you see the number of state expansions with A star and LMCut of the very basic variant and the most fancy variant. And you see clearly that this really pays off. And also in terms of runtime, this then translates to big advantages. Okay, so to conclude, as you have seen in the evaluation, it's always good to compare all member state costs in optimal planning and also to use the G adaptation. Duplicate checking most of the time does not pay off, but there are some special cases where it does. The implementation optimizations have some mild advantage, so it's always advisable to use them. And I'd like to conclude the talk with some ideas for future work. One example would be the combination with the quantitative dominance pruning, where you can get even more information, so make the pruning stronger. The other one would be to use EV MDDs to represent decoupled states. Thank you.